Hi everyone, welcome back. Today I am going to demonstrate the relationship between voltage, current, and resistance, which is a concept that in electronics they call Ohm's law. And to do this demonstration, I am going to take this hammer and I'm going to hit this piece of wood really hard. Now what do we expect is going to happen? Logically, we would probably expect the piece of wood to go flying off the end of the table. Well, let's see if that really happens. See if I can hit it on the first try. Yeah, sure enough, that's exactly what happened. Now why did it move? Well, it moved because I hit it with the hammer. I applied a force. Now in electronics, the idea of force is what we call voltage. If you watched my video about the analogy of the car tire, when I applied a force, motion began to occur. That's exactly the same thing that happened with this piece of wood. When I applied the force, the motion occurred. Now it moved across the table. Now we know that there was motion, but that doesn't really seem logical because or at least a good analogy, because in a wire, the wire doesn't move. You apply the force, you don't watch the wire fly across the table and onto the floor, but there is motion occurring. The motion is the motion of the electrons inside the wire. It's just a little bit harder to understand and visualize because we can't see the electrons moving, but they certainly do move. Now it doesn't take a whole lot of force to move an electron. They're tiny and they have very little mass. It doesn't take much to get them going. But when we need something to happen with electricity, we don't just need one electron to move. We don't just need 10. We just don't need a trillion. It's trillions of trillions of trillions of electrons. Those all have to be moving in order for something to get done, for us to accomplish work. So in terms of the voltage, the amount of force that I'm hitting with, the more force I push with, the faster the motion occurs. Well, that's exactly the same in Ohm's law. They call it a direct relationship. The more voltage we apply, if we increase the voltage, we're going to increase the speed with which the electrons are moving. Now, a certain number of electrons, a massive amount of electrons, moving through a wire in 1 second, moving through a point in a wire in 1 second, they call that an amp. So the faster the electrons move, the more current is flowing. That makes perfect sense thinking about the harder I hit the piece of wood, the faster the wood molecules are going to move, much like electrons. Now let me go pick it up here. If I take a look at the end of the piece of wood, theoretically, I could count the number of wood molecules at the end of this piece of wood. It's a lot. There's a ton of wood molecules here. Just like in a wire, there's a ton of electrons. If you cut the wire and look at the number of copper atoms in there, the number of electrons is just massive. Now, if I push, give a nice, slow, steady push, which is what they call DC, direct current, is a steady push, I can see that the electrons that I'm pushing directly make their way across the table. But as soon as I begin pushing, it's not just these electrons that are moving. These electrons push these electrons, which push these, push these, push these, push these. But so that means that as I'm pushing on this end is also moving at the same time. That's very important with electricity because as soon as I apply the voltage and the electrons at one end of the wire begin moving, the electrons at the other end of the wire, which could be miles away, begin moving at virtually the same time. That's why when you flip a light switch, the light, no matter how far it is away, instantly turns on, even though the electrons from the switch really haven't gotten very far down the wire. Now, alternating current means a push and pull on the voltage. It's very, very fast. If I were to slow that way down, then it would look like this. Push, pull, push, pull. That's alternating current. Notice that the wood molecules down at this end really don't ever make it all the way down to the other end. They don't get very far. But they don't have to because these wood molecules push on these ones or push on these ones. So that means that as I apply the voltage at the generator, the hydroelectric dam in one side of the country, the electrons going through a light bulb in a house on the other side of the country immediately begin moving. That's called propagation of energy. We just push in one place and the electrons way down at the other end of the wire begin moving nearly simultaneously. It's not quite the speed of light, but very close. Notice though that the electrons themselves, which is like the wood molecules down here, really aren't moving very much. They're actually moving pretty slowly. but the instant I move them here, the motion also occurs down here. That's why they're kind of two speeds of electricity. Now what about the resistance part? Because yeah, I can see how I apply more force, whack it really hard, and it's going to go a lot faster. Sure, that's obvious. So increased voltage increases current. Resistance is really just like friction. And when I gave this one a push, the surface of this table is pretty smooth. So when I give it a push, it moves pretty easily. There's not much resistance or friction. Now if I were to take the bottom of this and cover it with sandpaper or even like rubber or some sort of glue and then tried to push, what's going to happen? Well, I'm going to have to either push a lot harder to get it to move, or I'm just going to have to accept the fact that it's going to move slower. That's just like in a circuit. When you increase the resistance of a circuit, the speed of the electrons or the current slows down. Now, it could reach a point where the resistance is so high, it's like a brick wall. No matter how hard I try and push against that brick wall, it's not going anywhere. That's what they call an infinite resistance. Current stops. An open switch, like a light switch that's turned off, is like that brick wall of infinite resistance. Insulation is another infinite resistance. You can push as hard as you want and nothing's going to happen. Usually though, there is a breaking point, just like if I have this piece of wood up against a brick wall, now if I can get a sledgehammer and hit it, it will eventually move. I'm going to have to really hit hard, but it's eventually going to move. That's the same with voltage. If we have an infinite resistance or an open switch, insulation, and we push really, really hard, nothing's going to move until the point where we give enough voltage that it shoves its way through, a spark occurs, and damage can happen. That's what happens when a high voltage spike hits something. It can jump and cause sparks, which is current traveling where there's an incredible amount of resistance. So usually a switch or a contact of some kind, insulation, will have a voltage rating that's a really large number, hundreds or even thousands or tens of thousands of volts, and as long as you don't exceed that, you can't push through that brick wall. So this kind of illustrates the three main concepts of electricity. Voltage is the hammer. We have to apply more voltage or more force to get the motion to happen faster. Resistance fights against the motion. It's just like covering the bottom of the piece of wood with rubber or sandpaper or really rough surface or even a brick wall. More resistance will slow down the motion. In other words, more resistance will decrease the amount of current. So if we want more current to travel, that means we either decrease the resistance or we increase the driving force or the voltage. Current is usually the result of something happening. As long as we have voltage and little resistance, current is just going to naturally occur. So most of electricity is really figuring out how do we get the amount of current that we need. Well, again, we either do that by increasing the force, the voltage, or decreasing the resistance, and either one of those is going to give us enough current to get the job done. So I hope this analogy makes sense. There's a lot of different ways to visualize electricity. It's hard in itself because we can't see the electrons moving, but hopefully this brings some clarity, some question about how does motion occur and what's the relationship between voltage, current, and resistance. And I hope you enjoyed the video, and as always, if you have any questions, just feel free to ask. I can always address them in other videos or find other ways to relate this all together. But as always, go build something awesome. Have a great day.